So in previous video, we have seen that how the input xi is being arranged with the help of these gates. So we have formed a Boolean function, and based on that Boolean function, we have we have chosen the gates AND gate, OR gate, and NOT gate were chosen to implement this Boolean function for xi. Yi, it is same as that of the arithmetic circuit, so no changes is there for Yi. Just what is that true or complement circuit is being used over here. That is the function was like S0 Bi, S1 Bi complement. So here OR gate is used because it is being ORed. So OR gate is being used, and then two gates are there, AND gate are there because two terms are there, and Bi will be given as an input to one AND gate. Bi complement is given as an input to another AND gate. Okay, and then S1. So here S1 will be together with this Bi complement. So S1 will be together with this Bi complement. So from this S1, it comes over here and will be given as an input to the Bi complement. Okay, then S0 will be given as an input to the Bi. S0 given as an input to Bi. So it is before moving to that NOT gate, it will be given as an input to Bi together with Bi to the AND gate. Okay, so that is a combination, and both the outputs of AND gate will be given as an input to OR, which will be given as an input to the full adder, second operand Yi. Okay, so in Xi and Yi, Xi and Yi, they are making use of this S1 and S0. They are sharing the selection inputs S0 and S1. So in order to connect it between those two, you can take the inputs from here. That is this S1 and S0. It is being given to this NOT gate, and again it will be fed as an input to another AND gate like this. Okay. Hence it is being shared by the that is a full adders, that is the arithmetic circuits as well as the logic circuits. Okay, and from this yi input is over. Now next function is like zi is equal to s2 complement ci. So zi is equal to, zi means the c input. This will be taken as zi will be equal to S2 complement Ci. So what does that mean? S2, if it is equal to 0, then Ci will be equal to 1. If S2 is equal to 1, then Ci will be equal to 0. This input will be equal to 0. Okay, if S2 is equal to 1, Ci will be equal to 0. If S2 is equal to 0, Ci will be equal to 1. So here it will be S2, if it is moved to this AND NOT gate, here it comes and will be fed as an input to the AND gate. So Ci, if it is equal to 1, both the inputs, if it is equal to 1, then only Zi will be equal to 1. If S2 is equal to 1 means it won't be going over this line to this AND gate. It won't be going. It will be just giving as an input to the AND gate over here. Okay. So that is the logic behind that. So this AND gate will get activated only if S2 input is received. And S2 input will be received to that, will be given to that AND gate only if S2 is equal to 0. If S2 equal to 1 means what happens? If S2 equal to 1 means through this NOT gate it becomes 0. So here it becomes 0. So 0 if it comes over the AND gate means all C in always it will be equal to 0. If S2 is equal to 1, through this line it becomes 0. Once it reaches to this AND gate, checks the next input. That also if it is equal to 1 or 0, the output will be equal to 0 only. So this is the inputs of the full adder circuit. So based on the n-bit ALU that need to be designed, the full adder circuits will be cascaded to implement the same. Okay. So the output of each full adder will be fed as an input to the second full adder. So as said earlier, when S2 is equal to 0, the circuit, it chooses the logic operation circuit to perform. So these functions can be reduced like this. Xi is equal to AI, Yi is equal to S0 Bi, S1 Bi, and Zi is equal to Ci. So these are the functions which will be used to perform the arithmetic circuit alone. Okay, so these are the functions which will be used to perform both arithmetic as well as the logic operations. So if logic operations alone, if it need to perform means, then S2 will be equal to 1. So in that case, for S2, S1, S0, if it is equal to 101 or 111, the function will be reduced. That is, Xi can be written as AIYI, which means S0 BI. It is substituting this S0 BI, S1 BI, S1 BI complement Zi. So here you make the change like this. Xi is equal to AI. That is one function. Okay. Then Yi is equal to S0 Bi, S1 Bi complement. That is the second function. And Zi is equal to 0. So this is obtained by substituting the value of these S2, S1 and S0, that is 101 over these equations, onto these equations or to these functions. If you substitute and see, you will be getting these outputs. Okay, so the logical operations that are generated when S2 equal to 1. And if the combination is like this, you will be generating the functions in this form, 3 different functions. Okay. So with this, the function table of the arithmetic and logic unit can be defined like this. So here you can see that if S2 equal to 0, if S2 equal to 0, then it performs the different arithmetic operations. And if S2 equal to 1, it performs the different logic operations. Okay. And if S1 is equal to 1, then it performs what? The minus operations will be performed. S1 equal to 1 minus operation A minus B, like that. And if both S1 and S0, if it is equal to 1 means just performs the transfer operation that we have seen in the previous slide. And one more thing that you can see over here is related to the logic operation. If S2 is equal to 1, then the carry in, it is a don't care, it won't be considered. If S2 is equal to 1, then carry in input will not be considered. So don't care. The other things you have seen earlier. So this much is related to the arithmetic logic unit design. So what we have done till now is first we have learned about the processor organization, which includes the bus organization, accumulator. Those things were included inside the processor organization. And then to design the arithmetic and logic unit, we first design the arithmetic unit, and then logic operations were implemented on this arithmetic unit, making the carry inputs to 0. Observing the changes to be implemented, modifications were done on the arithmetic unit such that it gives the output of the required logic operations. And hence, we generated a final ALU design which implements both the arithmetic as well as logic operations based on the selection input S2. If S2 is equal to 0, this circuit, it implements the arithmetic operation, and if S2 is equal to 1, it implements the logic operations.